I wanted to share this assembly emulator and visualization tool that I co-developed that I think can be helpful for learning assembly language, especially memory allocation on the stack. Right now, the tool supports the ARM and x86-64 instruction sets. Before I show some of the features of the tool, I want to talk a little bit about what assembly language is and why I think it's important. Assembly language is the lowest level human-readable programming language, and there's roughly a one-to-one mapping between assembly and the underlying machine code instructions, which are the ones and zeros that the processor operates on. But there's not actually just one assembly language. Different CPUs have their own instruction sets. For example, there's ARM, x86, RISC-V, MIPS, PowerPC, and many more. When I say assembly is a low-level language, I mean it's closer to the underlying hardware. Different programming languages have different levels of abstraction from the hardware. For example, Python is very high level, while C and C++ are closer to the hardware, and assembly is even closer. There are pros and cons to each level of abstraction. One of the benefits of assembly is that it can be highly optimized, and therefore potentially run more quickly and efficiently than higher level languages. Although compilers these days are pretty good, and a hand-optimized assembly program might not be significantly faster than a well-written C program. The drawbacks of assembly are that it's harder to program in, and it's less portable than higher level languages because it is hardware specific. For example, if you write an ARM assembly program, it won't work on an x86 processor because the instruction sets are different. So why should programmers still learn assembly? Because if you don't know assembly, you don't know what the computer is actually doing. Knowing assembly makes you a more well-rounded programmer and gives you a more complete framework for how a program actually runs. So with all that out of the way, let's take a look at the tool. The info page has a list of supported instructions for ARM and x86-64, as well as a description on how to use the stack visualization feature and text editor. Now let's look at the ARM page. You can see a text editor, the stack, and the register file. The register file can be viewed in decimal or hexadecimal. You can see the general purpose registers, the frame pointer, the stack pointer, the link register, and the program counter, as well as links to the GitHub page and this YouTube video. You can click Generate Sample Code to generate a sample program for you to run. Let's look at factorial. You can either run the program, which will display the end result of the stack and the registers, or you can visualize the program, which will step through at a constant rate and update the stack and register file accordingly. You can also choose to step through manually. Let's see what that looks like. So first we move a value of 5 into R0. This is the input to the factorial function, so we're computing 5 factorial. Next, we're doing a branch and link to the factorial label. When we do that, the address of the next instruction, which in this case is line 4, is put into the link register. So we can go to this instruction after we've finished the factorial function. Next, we push R4, the frame pointer, and the link register onto the stack. Compare R0 to 1 and branch to this label ret1 if it is 1, and that's the base case. Since it's not 1, then we go into the recursive case, move R0 into R4. You can see that R4 is now 5. Then we subtract 1 from R0, and then go back to factorial, and then push R4, the frame pointer, and the link register onto the stack. And we continue this loop until now R0 is 1. So now we branch to return 1. And as you can see here, we've pushed all the values that we're going to multiply together onto the stack. So now we're going to move 1 back into R0, and then we're going to go and pop all the values off of here and multiply them together. So BXLR means we take the value in the link register and go to that instruction. So now we're going to instruction 11, and we multiply R0 and R4 together. And we continue this loop until the result is in R0. Now we're done, so we branch back to finish. Now let's see what that looks like for x86-64. So in x86-64, there's also some general purpose registers, RAX, BX, CX, DX, RSI, DI, and then R8 through R15. And now instead of the frame pointer, there's the base pointer, there's still the stack pointer, and then instead of the program counter, there's my personal favorite register, RIP, the instruction pointer. And you can also view these in hexadecimal. And with x86, it's slightly different because each of these registers is 64 bits rather than 32 bits in this particular ARM representation that's on this website. And you can also access either the bottom 32 bits, the bottom 16 bits, or the bottom 8 bits of each of these registers independently using a different prefix for the registers. So for example, instead of RAX, which accesses 64 bits, EAX would access the bottom 32 bits of the register. So now let's step through this program and see what it does. So first we push the input 5 onto the stack and call fact, which jumps to the fact label and pushes the return address 4 onto the stack. Now we're going to push our BP onto the stack, move RSP into RBP, starts the stack frame, and get the input, which is at RBP plus 16, and put that into RBX, so RBX is 5. Now we're going to do a similar loop to before, where we're going to push all the values that we're going to multiply together onto the stack. So now RBX is 1, and all the values are on the stack. So we're going to jump to ret1, move 1 into RAX, and the leave instruction just sets RSP to RBP, and then pops from the stack and puts that into RBP. So now RBP is 4000, and then ret just pops from the top of the stack and goes to that instruction. So now we're at 14, and we're going to go to the loop where we multiply all the values together and pop from the stack. So now the return value is in RAX, which is what we expect, and we're going to jump to finish, and that's it. So if you found this interesting, I put links in the video description to the Assembly Emulator website and the GitHub repository in case you want to look at some poorly written JavaScript. Thanks for watching, and I hope this tool can be helpful.